Well, welcome. In this video, as you can see, we're going to be looking at lesson 6.3, which is all about what we call counting strings that include replacement. And I'll define better what that means here in a minute. But first, let's look at what we have in this box, the multiplication counting principle. Now remember, in the previous lesson, we learned about what was called the addition counting principle, which we used in situations where we had the word or to represent either mutually exclusive events or overlapping events. So remember, we had both of those addition counting principles in the previous lesson. So to distinguish, these are, again, this is the multiplication counting principle, which says that if we want to find the number of ways to choose one element from event A, or from element A, and then one more element from element B, we would multiply those two numbers or expected outcomes. So here we're choosing one item and another, as opposed to the addition counting principle is looking at selecting an element from one set A or from the other set B. So make sure you don't get these confused. Okay, so let's see how we can use that for this the Price is Right example here. Now, I don't know about you guys, but whenever I was sick and I'd stay at home, there wasn't a whole lot to watch on TV, so one thing I enjoyed watching was The Price is Right. And so there's always the spinner that selects who goes into the prize round. And in that spinner, there's 24 congruent sections, numbered like the picture on the right there. So again, each contestant can spin the wheel twice. So in this case, a sample space for this experiment is going to be the number of elements in S. So we wanted to figure out how many total elements there are in this sample space. Which again, that means that we're going to have two spins. We're going to have our first spin and the second spin. Now the contestant doesn't have to choose a spin each time, but we want to just figure out how many total possible outcomes there would be if they did spin the spinner twice. So on the first spin, there'd be 24 options, and there'd be 24 options on the second spin. So at the total, we would multiply those, because again, this is an AND situation. We're spinning once and another time. So we'd multiply those together, we'd find that there's 576 elements in the set. Or in this next example, a lottery game played in some states involving picking 3 digits from 0 to 9 in order. So to describe a sample, we want to describe a sample space for this experiment and determine the number of elements in the sample space. So in this situation, we're going to have 3 numbers that are drawn. Now each of those numbers could be a digit from 0 to 9. So that means that each of those have 10 possible digits because we're counting 0. So we're not starting at 1, so there's 10. So 10 times 10 times 10 is obviously 1,000. So there's 1,000 elements in that sample space. So this brings us to a string. When the symbols in a problem must be ordered, it is common to refer to the ordered list of symbols as strings. The number of symbols in a string is the length of the string. Now that might not make a whole lot of sense. Let's look at this formula, and then I'm going to show you how we could use strings to make problems like the previous one and other ones a little bit easier. So again, these are strings with replacement. What that means is that once we choose a number or choose a letter or whatever the item is, that item is put back into the set for the next draw. So let S be the set with n elements. Then there's going to be n to the k possible strings, where n represents the number of elements in each string, and k represents the number of repetitions, or the length of those strings. Here's what I mean. Let's look at this example. Let's say we're taking a 10-question multiple choice math test. Each question has 5 choices. How many possible completed answer sheets are there? So now we could tackle this problem the same way that we did with the previous examples and say, well, there's going to be 10 questions. Each of those questions have 5 choices. So we would multiply 5 times itself 10 times. Well, clearly, we could also use exponents here to say that we would have 5 to the 10th power. So how does this connect with the string? So here, the length of the string is 10. Because there's 10 questions on the quiz. N represents the number of choices each of those questions would have. So we would write this as 5 to the 10th power. So if it's easier for you to think of it using exponents, that would be one way we could do this. Even if sometimes if you get stumped and you don't know how to write it with an exponent, you can at least start writing it out to see what number is being repeated. So then you can see that it's going to be 5 to the 10th and not 10 to the 5th power. You don't want to mix that up because those would give you two different answers. So 5 to the 10th power ends up being 9,765,625. Kind of runs off the screen there. Now, if we wanted to guess randomly on each question, what is the probability of answering all 29 questions correctly? Well, there's only going to be one correct answer sheet out of all of those. So you'd have a 1 in a 9,765,625 chance. Not very likely. Okay. Let's look at this next example. Why don't you guys go ahead and try this one on your own? So you can either do it like we did with the first couple of problems, or if you want to try it using that using exponents, you could do it that way as well. So why don't you pause the video and see if you can't get this one right. Okay, let's see how you did. So it says 3 of the questions on a science test are multiple choice with 4 choices each. How many ways are there to answer these questions? So again, we could do that doing it the way that we did originally, saying that there's going to be 3 questions. Each of those questions have 4 choices, so it would be 4 times 4 times 4. Or you could use exponents to say, okay, there's going to be 3 questions, so that means my exponent's going to be 3. Each of those questions have 4 choices, so that's what n is. So 4 cubed, either way, gives us 64. Let's see if we can't apply this to the next couple of examples. So the next one says, in a certain state, license plates have 2 letters followed by 4 digits from 0 through 9. We want to figure out how many different license plates are possible. So again, we could do it this way and say that we're going to have 2 license plates. They're going to have letters. Then we're going to have 4 license plates that are the first two items on the license plates are letters. The last 4 items on our license plates are numbers. So there's 26 letters in the alphabet. So we would have 26 times 26 followed by 4 tens. 10 times 10 times 10 times 10. Or we can use exponents and say we'd have 26 squared. So there's 2 spots on our license plates that have letters. And there's 26 letters to choose from, so it'll be 26 squared. 4 places on a license plate is going to have numbers. 10 choices from 0 through 9, so it'll be 10 to the 4th. Either way you set this one up, we end up with 6,760,000 different license plates. Now if you think about that, and let's say if the state is California, those license plates are going to go disappear rather quickly, especially when you have people that might have more than one vehicle. So that may not be enough license plates. So let's say if we expand that out to have 3 letters followed by the same 4 digits. So just adding a 26 in here and including an extra 26 in here increases our answer to be 175,760,000 possible different license plates. So almost 170 million more license plates just by adding 1 more letter. Pretty cool. Now, we can think of 2 events, A and B, as being independent if the probability of A does not affect the probability of B. To find the probability that a number of independent events all occur, you can apply the multiplication counting principle. So again, giving us a visual here, events A and B are independent events if and only if the intersection, so of A and B happening at the same time, is equal to the probability of event A times the probability of event B. So if that is a true statement, then those events are independent. If that's not a true statement, then they are dependent or not independent events. So let's look at these examples. This first one says the spinner here is used in a carnival game. It is assumed to be fair. The game consists of 2 spins. You win if the first spin stops on an even number and the second spin stops on a multiple of 3. We want to figure out what's the probability of winning this game. So again, we have 2 events. The first event is the probability of getting an even number. The second event is a probability of getting a multiple of 3. So now we have if you look at that spinner, there are 3 numbers that are even. So I have a 3 in 6 chance of getting an even number. Multiples of 3 are 3, 6, 9, 12, and so on. So numbers that 3 divides into evenly are multiples of 3. There's only 2 multiples of 3 on that spinner out of 6 outcomes. Now technically it'd be a lot easier to multiply these if we reduced them first. But since these are small enough numbers to work with, let's just multiply these together. We get 6 over 36, which reduces to 1/6. Always reduce your fractions. Now let's look at this last example, or this next example. It says in a certain spinning wheel there are 20 sectors of equal size. In 18 of those sectors you win a prize. But in the other 2 you lose all your winnings. If the wheel spins randomly, what is the probability of winning 5 prizes and then losing on the 6th spin? So here's the way that's going to work. We're going to set this up like this because we can use exponents here to make it a little easier. Because again, we're spinning 5 times, so our string is 5. Each of those times we spin, we have an 18 in 20 chance of winning. Now on the 6th spin, we're going to have a 2 in 20 chance of losing. And if you multiply those together, this time around we're going to write this as a decimal, a 0.059 or 5.9%. Which isn't something we've really talked about so far. A lot of our answers, we just left them as fractions. Really, it doesn't matter. You can have your fraction rewrite your answer as a fraction or as a decimal or as a percent. All of those are right. Unless the problem specifically states to leave your answer as a fraction or to write it as a percent. But otherwise, really any of those would be an option. So let's end this video by looking at this next final piece. So this is looking at dependent events. So events that are not independent are obviously dependent events. Now just to review, from the previous page, remember we said that events are independent if and only if this statement is true. Taking the probability of event A times the probability of event B and it equaling the probability of A intersect B, or A and B happening at the same time. So let's see how we can use that with this final story problem. So here it says a spinner is used in a carnival game. It is assumed to be fair. The game consists of 2 spins. You win if the first spin stops in a number or on an even number and the sum of both spins is greater than 8. We want to show that the 2 events are dependent. So if they're dependent, that statement above, as far as them being independent, is not going to be true. So in other words, they're dependent if the probability of event A times the probability of event B does not equal the intersection of the 2 events. So how does that apply to this story problem? Well, in this story problem, we can say that event A is a probability of getting an even number on our spin, and event B can be getting the sum greater than 8. So we want to see that multiplying those 2 probabilities together is not going to be equal to having an even sum greater than 8. Now, since we're dealing with sum of our spins, sum being SUM, we can go back and look at that dice card that I gave you. So let's take a minute to look at that. So even though this problem isn't talking about dice, it's dealing with 2 spins though, and the spinner has 6 sections. So really they could have used dice in this problem instead of a spinner. But again, the first event is the probability of getting an even number. Well, that happens half the time here. So that happens 18 out of 36 times. Or 1/2 the time. So we can reduce that. 18 over 36 would be 1/2. Now the probability of getting a sum greater than 8, if you look at your sheet where it's a sum greater than 8, that means that it's going to be a sum of 9 or more. And if you count those up, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times out of 36. But 10 over 36 reduces to 5/18. So that's where we get that from. And if we multiply those together, we're going to get 5 over 36, and that doesn't reduce. So now we've got to see, is that equal, or technically not equal to what we have on the other side. And I just noticed that I wrote this down wrong. It should have been that instead of being even and a sum greater than 8, it's supposed to be the first spin is going to be even, and the sum is going to be greater than 8. So we're looking to see if that intersection should not be equal to 5 over 36. So let's look again at that dice sheet. So if you notice, I've highlighted those that where the first spin was even and the sum is greater than 8. And that happens 1, 2, 3, 4, 5, 6 out of 36 times, which reduces to 1/6. So we can see that even looking at 536 and 636, that those are not equal. So we have been able to confirm that yes, these two events are dependent on each other. So they are dependent. So that's it. That concludes this lesson, lesson 6.3. So with that, good luck now as you work on this assignment.